Hello. We are about to continue a little bit with vectors in the plane. We did a bit in our live class today, and you know, some of the stuff that I intentionally didn't cover in the live and probably won't cover on this video would be your basic scalar multiplication with vectors and vector addition, which I know that you can figure out from looking at those formulas in the book and those properties. So again, if you have questions, I'm here for you on that. I just really think once you look at a couple of those examples, that's gonna come right back, and you're gonna remember that from learning vectors in pre-calculus. So I'm gonna focus our video here on just a little bit of the continuation of what we started in class. If we got to this definition of rectangular versus polar, fantastic. This might just be a repeat of that. If we didn't have time for it, then here it is. Rectangular is the standard form or component form that you are accustomed to, because this is basically what we all learn when we first learn about vectors. So it can go by any of these names. Our book may more often than not refer to it as rectangular form. But really, I would say I probably typically refer to this as component form, because you're getting the components from that head of the vector being right at 0, 0 or origin. Okay. And so then the components we're talking about is, what direction in X and Y are we headed for the tail? That's component form. So when you see that form, you're going to see the pointy braces that denote that we have a vector here. And you're going to see it by whatever change in X we have for the X component. And you're going to see it with the change in Y that we have for the Y component. Those changes are, the change that we see from the origin. And so that's why we notate it that way. A lot of what I also do, I prefer component form when I'm going to write out vectors. They look like an ordered pair. So it kind of makes our work a little bit easier to write them in this way. You are obviously free to use either one of these forms. I am perfectly happy with either form of a vector here. Some people have preferences, some people go back and forth, and that's totally fine. The polar form, we use the two measurements of our vector to write in polar form. Those two measurements are magnitude and direction. So magnitude looks like this in our book. It's got the two lines on either side of our notation for vector v. Now, if you're looking at any of our CU Succeed documents, which you will see quite often because I use different stuff from the CU Denver course, magnitude is written with just that single line on either side, which to me looks a lot like absolute value. And there are some texts that do use that for magnitude, and I won't, just because I'm going to try and stay consistent with our textbook. But just note that that is another way of writing magnitude. When we find magnitude, this is going to be a review from today as well, but our answer is always a scalar. And remember, when we're talking scalars in vectors, that's just our word for a constant. So like earlier when I referred to scalar multiplication, it's taking your vector and multiplying it by a constant, okay? And so we talk scalars when we're talking vectors, and that's just, our word that we use for that. So our answer here is a scalar, and then the other measurement would be our direction. So we are going to also use a direction angle. And that angle is basically our distance here from our positive x-axis. And the way in which we find that direction angle, we measure it using theta. This is another pre-calc concept that maybe you remember, but it is the arctan of y over x. And that, again, that is just a pre-calc notion there that takes my vector. If I'm finding this angle right here, my change in y would be this opposite side right here. So that's essentially my y coordinate of my vector. And it's that change in y. And because this forms a right angle here with my change in x or my x component, I'm taking opposite over adjacent, which is arctan. Okay, so just quick review of that, but that's how you find your direction angle right there. Okay, so the way we take these two ideas and put them into polar form is we say our vector v looks like this scalar multiple of our magnitude multiplied by our vector cosine theta sine theta. Okay, if you're really savvy here and you notice this little portion is what's called a unit vector. We're going to talk about that in just a second, but it's the idea that cosine theta sine theta lives on our unit circle. Our unit circle has a radius of 1, therefore a unit vector will be a vector with a magnitude of 1. So then by taking our magnitude and treating it as a scalar multiple to each of those components, we can find vector v by just multiplying that through. So that's the other way that you see it, is that vector v, we would take the magnitude of v times cosine theta, comma, the magnitude of v times sine theta to get more specific with those x and y components on vector v. Okay, so either way, you can leave it with the unit vector separate here with the magnitude out front, or you could just scalar multiply it through. So we're going to do a little practice here. We're going to write a vector that has a magnitude of 4 and a direction angle of 2 pi over 3. And I'm going to encourage you to pause the video and just go ahead and write that down real quick and write the vector in each form. Pause the video, write it in each form, and see what you come up with. Okay, so if you paused there and you wrote down polar form and rectangular form, I'm just going to go through those real quick. So rectangular form, first and foremost, just going in the same order as the last slide there, is going to look like V. And now this piece of it, and maybe I should do the polar form first and actually go a little bit out of order. But this is going to look like still my magnitude of V multiplied by my change in X and my change in Y. And so I probably, to backtrack a little bit, let's go out of order from that previous slide and just do our polar form first. So I'm going to actually just go up here to do that. All right, so polar form, probably a better place to start anyway, because here we do have the magnitude and we do have the direction angle. So that was my fault for not starting with that. Our magnitude of 4 is going to go outside, just to start with that notation. And inside of this piece here, we have cosine of 2 pi over 3, comma, sine of 2 pi over 3 that we want to go ahead and figure out those values of first. So again, this is my unit vector. This lives on my unit circle here. So it's just a matter of me remembering those ordered pairs. So that means we are taking 4 times, and yeah, really quick, I'm sorry. This would be good enough for polar form right here. Our goal was to bring it back to rectangular form. So this right here, you could leave this as your polar form. You could write it where 4 is multiplied through. That's your preference. To get this into rectangular form here, this is where we need to remember our unit circle a little bit. So cosine of 2 pi over 3, well, 2 pi over 3 is in the second quadrant, so that makes cosine negative 1/2. And in the second quadrant, sine is positive, so that would make this a positive root 3 over 2. And then if I were to distribute that through to simplify a little bit, then I'm going to go ahead and get rectangular form here for V as -2, comma, 2 root 3 when I simplify. So this right here would be good for your rectangular form. And, not that this unsimplified form isn't good. Obviously, our book is going to simplify things a little bit further than just leaving it at that. But, if you left it with the 4 on the outside, the magnitude of 4 on the outside, that would still be correct. Now, one additional note here, and this might be something that you remember as well, but we also learned something called linear combination form. Linear combination form, instead of keeping in component form, would use the idea that we can use this letter I to represent the unit vector 1, 0. So it is the unit vector in the x direction only that we call I. And then we call j the unit vector in the y direction only. So that's 0, 1. So what this does is this allows me to put an I next to any movement in the x direction and a j next to any movement in the y direction, so that I could also, in linear combination form, write this as negative 2I plus 2 root 3, and I'll put that in parentheses since that's kind of a mixed radical there, j. So no commas, no parentheses, no pointy braces, just a linear combination with I and j. All right. So last but not least, we talked a little bit about unit vectors and how they live on our unit circle. One of the things you will be asked to do is to write a unit vector. And so just as a quick review here, and maybe you remember, but the distinguishing factor of a unit vector is it has a magnitude of 1. So obviously any of the ones that are on our unit circle already qualify, but what if we have this vector right here, 5, -2, and we want to find the unit vector that goes in the same direction as that, but only has a magnitude of 1? Essentially, the idea is we are dividing out any existing magnitude that V has. So if we divide out that magnitude, that leaves us with a magnitude of 1. Okay, so we're going to go ahead and find the magnitude here. And this is a little bit of a review from our in-class portion today as well. Our magnitude formula looks a lot like Pythagorean theorem. So you can just think of doing Pythagorean theorem if you want. You can use that whole long formula that we wrote down. But really the idea is just, if we are in component form here, that this just looks like our first component, V1 squared, plus our second component, V2 squared, and that we take the square root of that entire thing, just like Pythagorean. So for our purposes here, that would be the square root of 5 squared plus -2 squared, which would be the square root of 29. And good news for you, maybe I brought this up in our live class or not. I'm recording this ahead of our live class, if you haven't noticed. But the good news for you, in Calc 3, we really do not care about leaving radicals in the denominator. So when you have something like the square root of 29, and in the past we've rationalized and we've gotten it out of the denominator, I am here to tell you that in Calc 3, we really don't have to worry about such things. We got bigger things to worry about, everyone. So we are not going to worry about getting radicals out of the denominator. The reason why I bring that up is I told you we want to take and divide out. In order to find my unit vector, I want to divide out any magnitude that V has from vector V. So I'm going to just go ahead and do V1, V2 here. I didn't understand. Oh my goodness. My devices keep listening to this video that I'm making and thinking that I'm talking to them. So that's just something that's happening right now. All right, so we are going to go ahead and take 1 over the square root of 29, and we're going to use that as a scalar multiple for 5, -2. So lucky us, we can just say our unit vector looks like 5 over root 29, comma, -2 over root 29, and because we have made it this far, that is sufficient as a final answer. I believe that that remains the case even with your textbook, that we have worked out solutions, and a lot of times the denominator will not be rationalized. It will just be left as radical 29 in the denominator. So, and obviously, you know what it looks like if there is a different answer somewhere on Calc Chat, say, or whatever, that, we would have 5 root 29 over 29 and then negative 2 root 29 over 29. So part of this is just we can leave our answer unsimplified or unrationalized and just know that we have to maybe determine if we have the same answer as our solutions manual has. So that's really it for finding a unit vector right there. Keep in mind with all of this talk that I've had about, not worrying about simplifying and stuff, that if you can simplify a radical, that you might want to do it just to simplify your overall answer for yourself. But if this is really all we're looking for, just leave it like that. And let me know if you have any questions. And good luck with these problems. We'll talk soon.